Okay, I'm going to do this problem involving Newton's laws here. So here's the problem. It's kind of a slightly tricky Newton's laws problem. You've got a 200-gram hamster sitting on top of an 800-gram ramp, and that thing is sitting on a scale. And the ramp is frictionless, so this here is frictionless. But this surface here is not frictionless, so this has friction. And so the block is held in place. If you think about if everything was frictionless, as the hamster slid down, the block would slide backwards to the left. But there's a friction coefficient between the scale and the ramp holding the ramp in place. Okay, so you've got two parts to the problem, part A and part B. Part A is what does the scale read in grams as the hamster slides down? So this is you have to think about how do I figure out what a scale reads. Anytime you have a problem involving the readings on a scale, you should know that the scale reading in newtons is equal to the normal force that it exerts. All right, so that scale is exerting a normal force upwards, supporting the stuff that's sitting on the scale. And whatever that force it exerts on those things, that will also be the reading on the scale. Okay, so we want to determine the normal force that the scale exerts on the ramp, and that will be the answer to this question. There's a little bit of a subtlety because this is in newtons. So if you want the scale reading in kilograms, you need to divide by a factor of g, the acceleration of gravity. Okay, so we'll get to that. We'll cross that bridge when we come to it. Okay, so what we should start doing is writing down a free body diagram, coordinate system, and Newton's second law. Since we're looking for something with forces, we should definitely sort of start thinking about Newton's laws. So I've drawn here the free body diagram for the hamster. The hamster just has two forces acting on it. The normal force from the ramp, so that I'm calling NH there, that's the force exerted by the ramp on the hamster. And then, of course, we have the gravitational force on the hamster. I'm using this sort of tilted coordinate system here. So this is a kind of standard situation of a block sliding down a frictionless ramp. And so we just need to write down Newton's second law in the x and the y direction. So let me do that. Since it's a rather standard situation, I won't spend too much time on it. So in the x direction, we just have the x component of gravity. Set that equal to max. We see the mass cancels out, and we get the kind of usual situation for something traveling down a ramp. Ax is g sine of theta. And in the y direction, we've got the sum of the forces equals to may, but that's 0 because the hamster is not moving off of the ramp in the y direction. So we just have the normal force has to balance the y component of gravity. So we have here nh is equal to mhg cosine of theta. Okay, so that's a pretty straightforward situation. We get those two equations, which I labeled 1 and 2. But things get a bit more interesting when we start thinking about the ramp. So I'll copy down these equations on the next slide, and then we'll think about what's going on with the forces on the ramp. So those on the previous slide, we worked out these two equations, which gave us these two relations, which I labeled 1 and 2 there. And now we need to do the same thing for the ramp. So the ramp, it gets a little more interesting. What are the forces on the ramp? There's a gravitational force downward. So we've got here the mass of the ramp times g. And then what else is touching the ramp? The scale. So the scale is going to exert a normal force upwards. I'm going to call this the normal force on the ramp, nr. Okay. What else is touching the ramp? The hamster, right? So the hamster is exerting a force this way. And now that's the tricky part of this problem. You think about it, what is this force? That's the force from the hamster on the ramp. That must be equal to the force that the ramp exerts on the hamster, equal and opposite, right? By Newton's third law. So the force that the hamster exerts on the ramp is equal and opposite to the force that the ramp exerts on the hamster. The force that the ramp exerts on the hamster is NH, right? That's this thing. So that means that this force that we just drew has to have a magnitude NH, right? In other words, this one here and this one here are a Newton's third law pair. They have equal magnitude and opposite directions. Okay? So that's why I'm using the same letter there. NH denotes the magnitude, so I use the same letter, and then the direction is clearly in the opposite direction, right? So this angle is theta again. And then what else? Any other forces? Remember, the ramp doesn't move, right? So the ramp remains in place. So if you think about it in terms of this coordinate system, x and y, that NH force there clearly has a negative x component, which has to be balanced by something, and it's not balanced in this case. The reason is that the ramp is held in place by friction, so there's got to be a frictional force going this way. We call it static frictional force, holding the ramp in place. Those are the four forces we have on the ramp. Okay. Okay, so now what we need to do is write down Newton's second law in the x direction and in the y direction. So let's start with the x direction. Sum of the forces in the x direction is the mass of the ramp times ax. But the ramp doesn't move in the x direction, so this is 0. So what do we have in the x direction? We've got Fs minus nh sine of theta equals to 0. And then in the y direction, sorry, I guess I should call this 3 and 4. Let me call it 3 and 4. In the y direction, I get is equal to the mass of the ramp times ay, which is again 0 because the ramp's not moving. And so in the y direction, we've got nr minus mr times g minus nh cosine theta equals to 0. So those are the four equations we get from applying Newton's second law to this system. So now on the next slide, I will just write down those four equations, and then we'll start thinking about how to solve the problem. Okay, so we've got all of the equations, we've done all the physics we can do, and now we just have to do some math, right? So part A, the question is, what does the scale read in grams? And I mentioned earlier that the scale reading in newtons is the normal force it provides. So we want the force that the scale exerts on the ramp, which is this nr here. So all we have to do is solve these equations for nr. So the first step would be to solve for nr from equation 4. So let me do that. And we can't quite put in numbers because we don't know nh in this equation. So then we'll just take from equation 2, we need to sub in what is nh. Okay, so let me do that. And then let's just clean it up a little bit. So we'll pull a g out and simplify those two cosines together. Well, there's a pretty straightforward formula for the normal force exerted by the ramp. At this point, you want to ask yourself, does this formula make sense? So it has the right units. Both terms have units of m times g, which is a force. That's in newtons. And the other thing you can check is, what if theta equals to 0? I get nr is equal to mh plus mr times g, because cosine of 0 is 1. That makes sense, right? Because if theta is equal to 0, remember this thing here is theta. That means the ramp is flat, and so the normal force on the ramp would just be equal to the weight, the combined weight of the hamster and the ramp. So that makes sense, right? So this is good. The other thing you could ask is, what if theta is equal to 90? I get nr will be just mr times g, because the cosine of 90 is 0. If theta is equal to 90, that means that the ramp is vertical. The hamster is just falling freely, right? So he's not exerting any force, just falling through the air. And so the scale would just read the mass of the ramp. So that makes sense as well, right? So at least the formula has the right units. It makes physical sense in those two cases, so we have some confidence in it. Now the only thing we have to watch out for is, remember, this is in newtons. So if I want the scales reading in grams, I need to divide by that g. Okay, so let me do that and plug in the numbers, and I'll let you see the final answer. So there you have the final answer to part A, 917 grams, somewhere between the mass of the ramp alone and the combined ramp of the mass and the hamster. So that makes sense. So now let's move on to part B. Okay, so finally, let's work on part B. What is the coefficient of static friction between the block and the scale needed to keep the block in place? So our goal here, our target, is the coefficient of static friction, mu s, right? And you look at these four equations, it's not in there, but you know that it has something to do with this Fs, right? Something to do with that force of friction. And you have to remember that for static friction, the static frictional force is less than or equal to mu s times the normal force, right? Which is acting between the two surfaces. So in this case, we're going to have the static friction is less than or equal to mu s times the normal force, and we called it nr, right? It's the force on the ramp. So we're thinking about the coefficient of friction in here on this surface. So we need the normal force that's being applied from the scale to the ramp. That's nr there. Okay. So now we just need to sort of combine everything together. I've got this equation for Fs less than or equal to mu s times nr. And so I will just take equation 3 and substitute it in. And we get here nh sine of theta is less than or equal to mu s times nr. Okay. And now we need to also substitute in nh and nr. Okay, so I just wrote out a couple more steps here. I took in, from equation 4, I substituted in for nr. And then from equation 2, I substituted in for nh. So we've got this formula here getting to the answer. What you notice is there's a g in every term, so I just get rid of the g's. And let's solve this for mu s. Mu s has to be greater than or equal to, on the top I've got mh cos theta sine theta, and on the bottom I've got mh cos squared theta plus mr. So there's our final formula for this problem. So we know all the numbers. We have, let's check the units. The units of mu s should be 0, or there shouldn't be any units. And it's good because on the top I've got kilograms, and on the bottom I've got kilograms. So that looks fine. Let's also again think of these special cases. Let's check. What if theta is equal to 0? I get mu s is bigger than or equal to You see I have sine of 0 in the numerator, so it's just going to be 0. So it just means that I don't really need any friction to hold it in place. And that makes sense because if theta is equal to 0, the thing is flat and it will just be in equilibrium. It'll stay there. I don't need friction to hold it in place. So that makes sense. You can also check if theta equals 90. Then I've got a cosine of 90 on the top, which is also 0. So that's mu s is bigger than or equal to 0, which is also also makes sense because if theta is equal to 90, the hamster is just falling, and I don't need any friction to hold that block in place. So that all makes sense. So now all we have to do is just plug in the numbers and find the answer. So I'll do that on the next slide. So there you have it. There's the answer. If you plug in all the numbers, mu s has to be bigger than about 0.107, which is a reasonable number. If you get mu s, which is much bigger than 1, it sort of causes you to question it. So this number seems reasonable. So it's a kind of tricky problem involving Newton's second law and Newton's third law. We had to use the action-reaction pair in a couple places. And I hope you found this video useful in solving these kinds of problems.